Neptune, the most distant planet in our solar system, has always held an air of mystery. Shrouded in methane-rich clouds and battered by winds reaching supersonic speeds, it has long remained one of the least understood giants in our cosmic neighborhood. Unlike Jupiter and Saturn, which are frequently observed, Neptune's sheer distance has made it far harder to study. That changed recently when the James Webb Space Telescope, humanity's most advanced window into the universe, captured something extraordinary: evidence of a massive collision with the ice giant. This event is unlike anything astronomers had anticipated and could reshape our understanding of how the outer solar system works. The telescope had not been searching for signs of such an event. Its mission primarily focuses on probing the early universe and scanning distant exoplanets. Yet during routine observations of Neptune's southern hemisphere, astronomers noticed something highly unusual: a sudden burst of infrared radiation. Neptune's thermal signature is usually consistent and cold, but this sharp spike revealed that something extraordinary had disturbed its atmosphere. When the data was examined further, the images revealed a massive disruption in the planet's upper cloud layers, too large and too sudden to be explained by internal weather alone. Analysis showed that an external object, traveling at incredible speed, had struck Neptune. Models suggest the impactor was between 30 and 50 kilometers across, likely a large asteroid or a trans-Neptunian object that strayed from its orbit in the Kuiper belt. The collision sent shockwaves racing through Neptune's atmosphere, displacing cloud bands and even disturbing its faint ring system. Infrared sensors revealed a new hotspot in the southern hemisphere, glowing far brighter than anything seen on the planet in decades. A haze of debris from the collision lingered in the upper atmosphere for several days, forming a faint arc visible in both infrared and visible light. Scientists believe the impactor was made of ice and rock, similar to the many frozen bodies that orbit beyond Neptune. It may have been a rogue Kuiper belt object nudged out of place by gravitational interactions before being pulled fatally into Neptune's gravity well. But what made the event even more astonishing was how the planet itself responded. Neptune's magnetic field, already highly unusual because of its tilt and instability, showed clear signs of disturbance after the impact. The charged particle environment around the planet shifted significantly, suggesting the shock may have penetrated deep enough to disrupt internal convection zones tied to magnetic field generation. This discovery has profound implications. For decades, astronomers assumed that catastrophic collisions like this were mostly confined to the early days of the solar system when debris was more common. The sighting on Neptune proves that such violent events still occur, raising questions about how many other large bodies may be wandering the outskirts of our solar system undetected. It also challenges our understanding of the current stability of planetary orbits and the behavior of distant icy worlds. The event carries another sobering reminder: if an object of similar size were ever on a collision course with Earth, the devastation would be beyond comprehension. Neptune's collision has become a kind of natural laboratory, giving scientists invaluable insight into how energy from an impact propagates through a planet's atmosphere, how debris disperses, and how magnetic systems can be disturbed. Every detail helps refine our models of planetary defense and collision dynamics. Ultimately, this moment marks more than just an observation of a distant planet. It is a wake-up call that the solar system is far more active and unpredictable than we like to believe. Neptune's collision is both a rare scientific gift and a stark reminder of our vulnerability within the cosmic arena. The recent collision on Neptune has not only stunned astronomers but also highlighted the limits of our current ability to monitor the solar system. The James Webb Space Telescope was never designed to track planetary impacts, yet it managed to capture one of the most significant events observed on a distant world in decades. Had it not been pointing at Neptune at the right moment, the impact might have gone unnoticed, its traces quickly erased by the planet's turbulent atmosphere. Ground-based observatories, no matter how advanced, would likely have missed the sudden infrared burst. This raises important questions about what other cosmic events may be slipping past undetected. For Neptune itself, the collision could leave lasting marks on its atmospheric dynamics. Researchers have already noted unusual wave patterns spreading across its mid-latitudes, indicating that the impact energy has rippled through the planet's powerful jet streams. Neptune's winds are among the fastest in the Solar System, and early measurements suggest they may have been temporarily deflected or accelerated. Even Neptune's faint and fragile rings showed signs of disturbance. Normally difficult to detect, the arcs within the rings brightened briefly after the collision, likely caused by debris kicked into orbit before being recaptured. Whether this will permanently alter the ring's structure or density remains to be seen. The chemical aftermath of the event is equally intriguing. Spectral analysis revealed a sudden increase in hydrocarbons and nitrogen-rich compounds not usually present in such quantities in Neptune's upper atmosphere. This could be leftover material from the impactor itself, or it may signal that the intense heat and shock triggered deeper chemical reactions within the atmosphere. Understanding these changes is crucial, since Neptune could serve as a model for studying the behavior of exoplanets under similar extreme conditions. Beyond Neptune, the collision has sparked renewed interest in comparative planetary science. Uranus, another icy giant with similar characteristics, has been far less studied in recent decades. By examining how Neptune responds to a massive impact, scientists can make predictions about Uranus's behavior under similar circumstances. This event is not just a glimpse into Neptune's hidden processes, it's a chance to refine theories about planetary evolution and dynamics across the cosmos. For theorists, the impact serves as evidence that the Solar System is still active in ways once thought confined to its early history. Models of planetary migration and debris scattering suggest that outer Solar System objects continue to shift and collide, even billions of years after planet formation. The Neptune impact reinforces the idea that the outer boundaries of our system remain in motion, subtly reshaping themselves in a long, ongoing dance of gravity and matter. Perhaps the most striking realization from this discovery is how quickly perceptions have changed. For centuries, Neptune was seen as a quiet, frozen giant at the edge of the Sun's domain. Now it has become the stage for a dramatic, high-energy event, proving that even the coldest and most distant worlds are still dynamic and unpredictable. The wider scientific community is already mobilizing to follow up. Hubble, along with observatories in Chile and Hawaii, has shifted focus to Neptune to track atmospheric and visual changes. Though they lack JWST's infrared sensitivity, their imaging in visible and ultraviolet light will provide valuable complementary data. The European Southern Observatory has also announced plans for spectrographic monitoring during Neptune's next opposition, when it will be most visible from Earth. Together, these efforts could reveal just how deeply this impact has reshaped the planet.